Welcome to another episode of Code for Thought. In this episode, you'll hear from Loïc Lannelongue, who I met at his college in Cambridge end of 2023. Loïc is a researcher in biomedical data science, but in fact, it was for quite another project that I went to see him, his work on making computing greener. Because Loïc and Michael Inouye, a colleague of his, have started a project called Green Algorithms. And one part of it is a calculator that allows you to estimate the carbon footprint and energy consumption of your algorithm and computing jobs. Making the environmental costs of computing explicit is an important step in raising awareness. An awareness that is often lacking when it comes to estimating the environmental impact that computing after all has. And I think that we as researchers and engineers do well in considering how we can make computing environmentally more sustainable in future. The project itself, Green Algorithms, has been making headways. Only a couple of weeks before this episode went live, Loïc and Michael have been awarded by the Health Data Research UK conference, HDR, with the annual Susannah Boddie Award for impact for their work on green algorithms. In addition to that, Loïc has been advocating a more sustainable approach to computing with fellow scientists, engineers and lawmakers. He's been to conferences and workshops like, for instance, the Collaborations Workshop of the Software Sustainability Institute in the UK in 2023 and has even been shadowing a Member of Parliament in early 2024. And so I was quite excited to make my way to the beautiful and ancient college that is Jesus College in Cambridge on a late November morning and talk to Loïc about his important work. So, hello Loïc.
Hello.
Thanks very much for your time, and we're here in this very nice college, Jesus College, and you've been here for 5 years, you told me beforehand.
Yes, I'm a postdoctoral researcher at the University of Cambridge at the Vielen Dank Research Institute doing computational biology. But I also spend a lot of my time looking at the carbon footprint of HPC. So basically spending half my time making myself feel guilty for what I'm doing in the other half.
Okay. And just a quick introduction. I mean, you already mentioned that you're working here in Cambridge and you've been here for a while.
Yeah, so my background is in applied math and statistics and machine learning. And for my PhD, I moved to the clinical school here in Cambridge to research computational biology. And halfway through, we had these terrible bushfires in Australia, which is part of our lab is based in Melbourne. So we have lots of collaborators, and we were doing these Zoom calls with collaborators, putting sellotape on their windows to keep the smoke out and things like that. So it kind of made us think, okay, we're using large compute and large algorithms for genetics all the time. Maybe we should be a little bit mindful of what the carbon footprint of everything we do is. And when starting working on that, we realized there was actually no tool to do it. There was absolutely no resources to estimate it. So what I thought would be kind of a few days side project turned into a 3 years slightly bigger project where we had to first build the tools and then think about how to mitigate the impact of our work.
So talking about the impact of the work, I mean, what is the impact in particular for high performance computing and the large engines?
Yeah, that's a tricky one. Data centers, so overall, we estimate that the carbon footprint of data centers annually is around 100 megaton of CO2 equivalent. For context, that's the same as the entire US commercial aviation in the same time. Now, obviously, not all data centers are doing high performance computing and science. And there aren't very good numbers about HPC in total, but we're starting to have figures about individual models. So, for example, everyone talks about ChatGPT at the moment. So there was a team who estimated the carbon footprint of GPT-3, which is the ancestor of ChatGPT. And they found that training it was about 500 tons of CO2 equivalent. And again, for context, the IPC tells us we should aim for about 2 tons of CO2 per year per person to keep global warming under control. So 500 is a lot bigger. Models like genetic models, they can reach dozens of tons. So we can easily be in the kind of tons of CO2 territory. Doesn't mean every model has an enormous carbon footprint, but the fact that these do probably means we need to be mindful about this.
So it is a problem. And the first thing that I have on my list that I want to talk about is the greener framework that I think you and other people developed. So what is that?
Yes, so after a couple of years building tools and trying to work on this, we realized it would be good to have a set of principles that are common to everyone and could guide the field moving forward, something a little bit similar to the FAIR principles for open data. Mm-hmm. And so we gathered different stakeholders, people from HDR UK, so research institute, but also funders and all levels of seniority to come up with a set of principles. We call that GREENER because we're scientists, we love a good acronym. So the first two are governance and responsibility, which is basically a way to say who is in charge and who can make an impact. And the answer is very easy. It's everyone from grassroots movement to top-down approaches. So we need to have also funders and research institutes involved. But grassroots movements and RSE and postdocs and PhD students are very, very important as well. The next ones are estimations, because we need to know what the carbon footprint is. And that's one of the big problems is we had no idea what it was whatsoever. So, we can't tackle a problem if we don't know how big it is. And that's what we've been working on with the whole Green Algorithms initiative, is to build these estimation tools. So then you can then report this impact. And when we talk about impact, it's important to consider both electricity, so the impact of using electricity, but also embodied impact, which means building the hardware, which has absolutely enormous impact.
And the cooling.
And the cooling as well. So that's, which is not only electricity, but it's obviously also water usage. So it's a very difficult field to navigate, but there are lots of impacts to include. One way to tackle those is, and that takes us to the end, which is new collaboration, is to... Because with HPC, we're so lucky that you can run an experiment anywhere. We've seen it with cloud computing. So it doesn't have to be in the room next door, which means you can make the most of using, for example, low carbon electricity in a different place. The only challenge to that is we need to be particularly mindful when we start to relocate compute and data, especially when it comes to low and middle income countries, because we don't want to kind of go there and say, give us all your compute and all your data. It's obviously terrible. So that's something to keep in mind. And then it just takes us to education and research. And education, because we need to include the notion that compute has a carbon footprint when we train people up in computer science and software engineering. And research, because there's still a lot we don't understand about computer power usage, as surprising as it may be. So actually our estimation tools do a good job and they're actually quite accurate, but they could be better if we could understand better how we can code more efficiently in some cases. So there's still a lot of scope for research.
And I think it comes at the right time because cloud computing, as you just mentioned, has gone up, and not just for scientific purposes, but also obviously for commercial purposes. There are a lot of commercial data centers out there. I want to focus a bit on the estimation bit. How can you estimate what the impact is? So you mentioned already different aspects of it. There's the energy consumption itself, so maybe we can start with that, but also things like waste and the manufacturing, etc. Yeah.
If we start with the electricity usage, so that's the carbon footprint of the usage phase. When you running a model, what's the carbon footprint of using your HPC server for a few hours? And that's actually surprisingly easy to estimate, because on one side, it depends on how much electricity we need. And the electricity only depends on the hardware and the software. So what kind of computers do you have available and what are you doing on them? How many cores you're using and what task are you doing? And once we figured out how much electricity is needed, then we need to figure out the carbon footprint of producing that electricity. This is something called carbon intensity of electricity. And that mostly depends on where you are in the world, because most data centers are plugged to the main power grid. So if you're in a country where the electricity mix uses a lot of renewable, the carbon footprint of electricity will be a lot lower. And that's where we can have extreme differences between countries, between the very low carbon countries, which can have a carbon intensity of around 20 grams per kilowatt hour, all the way to much more carbon intensive countries. For example, Australia is quite bad on that, where we can reach 700 grams. So by doing exactly the same thing on the same hardware, then you can just multiply your carbon footprint by 50 or 100 just by being in a different part of the world.
Yeah, so we're here in the UK. I think you're from France. France has a lot of nuclear power, which some people might consider greener, but certainly greener than
well, it's definitely low carbon.
It's lower carbon.
What we think about nuclear
greener.
Waste in terms of purely carbon footprint, it is low carbon,
But here in the UK, it's a little bit different. So how different is it between UK and France? Can you estimate that?
Yes. So if people are interested, there's this website called Electricity Map, which is really cool. And you can see in real time the carbon footprint of different countries, but you can also see where they are importing electricity from. Because, for example, Switzerland is a great example. All the electricity they produce is very low carbon because it's mostly hydro. The problem is they don't produce enough. To complement it, they will import coal-produced electricity from Germany. So the total usage mix is actually a lot higher than purely hydro. So France is lower than the UK as far as I've seen recently, and maybe half of the UK, maybe less than that.
Right.
But there are a lot of exchanges between countries, so that depends on the time of day. But France is doing well because nuclear is very stable as opposed to renewable energies. So it's a low carbon that they can rely on. Even within the UK, actually, it changes by regions quite a lot. In the UK, we're quite lucky that we have the ESO, so the power grid provider makes this data available, and there's a website called Carbon Intensity UK or something. So if someone is interested, they can check it out. And you can see region by region. So for example, Cambridgeshire is doing okay, but not great. But if you go in Scotland or north of England, it's absolutely brilliant because it's a lot of renewable there.
So the estimation then, going back to the estimation, data centers have 500 tons. So you mentioned ChatGPT, which produced 500 ton carbon emissions. So what should we aim for?
That's a big one. Data centers are getting about as efficient as they can be, because one of the things to include in how much electricity we need is the efficiency of the data center. So there's this number called PUE, power usage effectiveness, that data centers put on their marketing page everywhere, saying we're the best in the world, especially cloud providers. And that's a way to measure overhead. So basically it quantifies how much cooling you need per unit of compute. And historically, you would need double the electricity you need for your computer just for cooling. So, you provide 100 kilowatt hours, only 50 are being used for the computers. The other 50 is just for overheads, which is obviously a waste. Now, the best data centers have really taken down to maybe only 10% extra for cooling. And that's probably as good as it's going to get. We don't have as much improvement possible there because there's been really good savings done there. And it's interesting, the question about what should we aim for? I think it's a question of cost benefit. And that's a big part of what we've been talking about in the past few years working in this project. Is it's the same way with money. When we start a research project and we apply for a grant and we say, I need £500,000 to do this project. What we're saying is we think the outcome will be worth putting that money in. Of course, there's no guarantee. It's research. We never know. But there is potential, and we can make, in a grant, we can make a reasonable case that it's worth giving us the money. And we believe it should be the same thing for carbon footprint. So, 500 tons, I'm not saying whether it's bad or good. It's a lot. That's a fact. The same way that £500,000 is a lot of money. I'm not saying, maybe if you can cure cancer for that money, it's not a lot at all. If you're just playing around and doing nothing, it's a lot of money. So, a lot doesn't mean much. It depends what you do with it. And if people could make a case saying that they need all that money, they should be able to make the same case to justify why having that big a carbon footprint. The problem is that in compute in particular, financial cost and environmental cost are completely decorrelated. So if you work in a university, compute is free, virtually, in most universities. I know it's not the case everywhere, and obviously we're quite lucky in the UK. But mostly for researchers, it's either free or at very, very low cost. So that's not the deciding factor. And usually if you apply for a grant, most of the money is going to go to staff or maybe a bit of storage. But it's not a lot is going to go to compute. Maybe a project, then you don't need to make as much a case for why the project is worth doing because you don't need as much money. Except if the project is coming with an enormous carbon footprint, the bar should be higher. And so what we're hoping to achieve with encouraging scientists to do this environmental impact statement, the same way we do financial impact statement, that we do ethical impact statement in medical research, is to say, well, even if a project is very cheap financially, but if it has a really big carbon footprint, we should be able to make a case of why it's worth doing. And if we can't make this case, then maybe we shouldn't do it. And it's not at all to say we shouldn't do science. I mean, I would be out of a job. I'm using machine learning quite a lot. But it's to say clinical research, we still do clinical trials, even though we accept that clinical trials have a downside for the patients. There is potential downside, but we think it is worth doing because the potential benefits are greater. Same thing with compute. There's a report from the Royal Society about new technology and the planet, and they're quite interesting. And I like the way they put it. They say new technologies, especially if they're developed for net zero, but in general, should be energy proportionate, which is there should be a reasonable assumption that their benefits are going to outweigh their environmental costs. And I think if we can kind of get in the habit of doing this process of thinking about it beforehand and acknowledging this impact afterwards, we would be in a much better place.
And I think that takes us to the new collaboration bit, or the funding bit at least, because you're talking to funders or funding organizations about this, how they're responding to that. Because there is the net zero, you mentioned that, and I was about to mention it as well, the net zero initiative in the UK. From your perspective, how are funders responding to that?
Yes, they're receptive. Obviously, changing any kind of funding rules is incredibly complicated. And, adding a question to a funding application is like a months-long or years-long process. So it's very complicated. And funders are careful on not adding red tape, so not making it harder for researchers to apply, which is a fair point. I think we're moving in this direction. And I think at some point it will be unavoidable that as part of an application, researchers have to acknowledge and estimate the carbon footprint of their research. But I think we're going to get there. It is a complicated topic. There was a really interesting use case. There's the French Department of the Environment, which is the equivalent of DEFRA in the UK. They put out funding calls the same way UKRI does in the UK. And there was one funding call for AI applications to local communities. So it's a way to how AI can make local communities more sustainable. It's a big call. It's like 40 million euros over 5 years. And they required that every single application has to have a section about environmental impacts of AI. And actually, it was quite nice because they made it compulsory for these to use our online calculator to estimate this impact. So now all the applications had to estimate the environmental impact of their models based on what they think the compute is going to be. And the interesting case is it didn't break science. People still applied because it's a big pot of money and it's worth spending half an hour, and people understood. There wasn't a big backlash against it. Researchers and scientists and companies that were applying, they understood that it was a fair request. So it's a really interesting use case that actually we can do it.
Indeed. So let's talk about your estimation tool itself. So people can go to it online, can they?
Yes. So if they just Google green algorithms, or I've been told we were like one of the first results, so it should be easy enough. But it's called the Green Algorithms Calculator. It's very much on the model of what flight calculators are, for example. So if you just go on the calculator, you can enter how long the model runs for. So, how long is your job on your HPC facility, what kind of resources it's using. So how many CPU cores, how much memory, what kind of CPUs these are, and where you are in the world. And then you can also customize a whole set of things if you need to, but you don't have to. And then it will give you an estimate of carbon footprint. That's the first tool we built, actually. We released it early 2020. It's because there was some trackers. So there are a lot of good tools that are packages you put in your Python code, for example, and they will track what you're doing. The problem with that is, you need to do Python and mostly machine learning in Python because a lot of these tools are built for that, which is fine, except contrary to what data scientists tend to think, a large part of computational science nowadays is not Python and is not machine learning because, it can be like chemistry simulations or computational biology or physics or astronomy or astrophysics. So all these things. And so the idea of the online calculator was to say, it doesn't matter what hardware you're using, it doesn't matter what software, it doesn't matter what field of science you are. There's a tool you can do to have a rough estimate of what the carbon footprint is. And that you can do either before running a computation to have an idea of what the carbon footprint will be, or just afterwards. And so that's been really interesting to see it being really picked up by a lot of people, finding it quite interesting to be able to see their carbon footprint. That works quite well. Now, online calculators, they have a problem, which is obviously if you run 100 different jobs with slightly different parameters and, they don't all have the same runtime. And I'm sure that's what a lot of listeners thought when I was describing how it worked. It's not very practical to plug one by one in the calculator. And so I came to the same conclusion and I was like, how can we make it easier for researchers? And it turns out everything we do on the cluster on an HPC server is logged because they need to charge us at the end. They don't charge us a lot of money, but most of what we do, usually there's a log somewhere that says this person used that many CPUs and that much memory for that many hours. And so here in Cambridge, we're using Slurm as a workload manager, which is getting more and more popular now. Everyone's moving to that. And I thought, all the Slurms are there. And so I thought we could just pull the logs and use the same formula, the same kind of green algorithms method, but estimate carbon footprint based on logs.
All right, okay, but you don't necessarily have the logs from people who go to the online tool.
No, exactly. So that's why we built this like green algorithms for HPC tool, which is kind of a slightly different tool. It's all completely open source. It's all on GitHub, so people can poke around. Yeah. And the idea was to say, now we have these two tools. So we have an online calculator to make it quick and easy. And for people who want aggregated statistics over a long period of time, say, what is my carbon footprint for the past year? Okay. They can use this kind of simple HPC tool that works quite well. And that's kind of one of the exciting development we're working towards is say, okay, how can we put a dashboard on that? How can we make it easier for people to have access to this information? Because that's what we found makes a big difference is feeding back the information to users. Because people in data centers and sysadmin who maybe listen to us, they will say, oh, but they've been thinking about carbon footprint for a long time. And that's completely true. And they've done amazing progress. But end users didn't used to have this information. And obviously, I'm not a software engineer by training. I'm more on the kind of science side. So I was like, users don't have this information, so they don't change their behavior because they don't realize what the impact. So that's been a big focus on this project was to say, how can we feed back information to users?
There was one thing that you mentioned. Machine learning is using Python a lot. That pops the question in my mind. Does it actually matter what language you use in terms of energy consumption?
Yeah, no, that's a very good question. And every time I give a talk, I usually have a question, someone bringing up. There's a paper that came out maybe a few years ago that ranked all the different programming languages based on energy efficiency. And they have a table where Rust and C++ is at the top in terms of efficiency and Python is all the way at the bottom. And that's a trade-off between how easy it is to code in it versus how energy efficient it is. There's no surprise here. I'd say yes and no. Yes, obviously, as this benchmark has shown, the language makes a difference and Python is a lot less efficient than C++. Now, it depends how you use it. So if you do machine learning in Python, you're not actually using Python because you're using PyTorch or you're using TensorFlow as packages, which have been optimized and optimized and optimized. And they are usually coded in C++ underneath. So actually, when you're using a package, you're just using a wrapper in Python for a C++ package.
Like NumPy as well.
Exactly, yeah. So you're having the best of both worlds. Usually my argument is if we were to force everyone to go back to C++ for the sake of energy efficiency, I would be so bad at it that it doesn't matter how good the language is. I would probably be a lot worse than using Python. Yeah. So yes, the language matters, but I don't think it's worth being too paranoid about it. What matters is actually whatever language we're using, because we usually have very limited choice. It depends what the community around us is using. We need to make sure the tools everyone are using are coded as efficiently as possible. You know, if you're doing your little analysis, it doesn't matter if it's using in R or Python. If you're building a package or a tool that you're hoping the entire community is going to use, something like PyTorch, then yes, if PyTorch is coded incredibly inefficiently, that's a problem. And I guess that takes us to the importance of research software engineers.
Indeed.
And there's this UKI net zero digital research infrastructure scoping project that just concluded recently, and they put out a report that's how can we take UKI digital to net zero. One of the main thing they push for is what they call green research software engineers. And that's the idea of saying that RSEs are very good people who are able to do all this efficient coding. The problem is we don't have enough of them. So much of science, when we said about PyTorch is kind of the exception where because there was a lot of traction, it's AI and everyone's excited, they managed to get actually really good software engineers to optimize the code. But so much of what happens in science, in computational biology or in genetics, because that's the field I'm in, you know, the tool is just a postdoc who kind of published a paper and published an R package alongside it. Yeah. But it's not efficiently coded, and there are orders of magnitudes of savings that can be made by optimizing the code. So I guess yes and no. The language matters, but what matters more is how we do the coding underneath.
And that's a nice segue into the next subject that we're going to discuss. How can you actually make your code more efficient?
So if we go back to the energy estimation we talked about, carbon footprint depends on how much electricity we use, and then the carbon footprint of electricity. But how much electricity we use depends on how much resources we use. So, you know, it depends on runtime, it depends on the number of CPU cores you're using or GPUs, and the memory used. Now, memory is an interesting one where the carbon footprint of memory doesn't depend on how much memory you use, but how much memory is available. So if you book 100 gigabytes on the server, it doesn't matter if you're only using 2 of them. Your carbon footprint will be roughly the same as if you were using the whole 100. And that's due to how memory is designed, like basically favoring speed of access over energy efficiency. So that's an easy saving. Don't request 10 times the memory you need on the server just to be safe and make sure the job doesn't fail. Or just optimizing coding. Sometimes, we've all done that. We had the option of spending half an hour optimizing our merge between different tables, or we're just lazy and we book 200 gigabytes on the server to do like a horrible massive merge where we need 200 gigabytes for 5 seconds. Writing more efficient code, either that codes that runs faster or that uses less resources, is one of the best things we can do. And that's an interesting trade-off because sometimes, you can make it run faster by using parallelization and using more cores. There's no right or wrong answer. There's usually a sweet spot that everyone's aware of. Maybe using 4 cores instead of 1 is massive gains. But then if you double again to 8, it's actually very marginal. You're only saving 2 minutes out of a 1 hour runtime. And these marginal gains are things we need to be mindful of. Because in this case, we're only saving 2 minutes, but we're still doubling our carbon footprint. So it's a trade-off, like most things. And other things we can do is actually be mindful of when we run a job on the server.
Okay, yeah. Because the energy that is being consumed is different at different hours of the day.
Yes, and it can change quite a lot. So for example, in the UK, it can vary quite a lot. It can go from single to double, basically, within a 24-hour window, depending on how much renewable energy is available. And in the UK, and some other countries are starting it, we have this tool online that put together a forecast of the carbon footprint of electricity over the next 48 hours. And that's actually something that came out of the collaboration workshop 2023 organized by the Software Sustainability Institute. So as a hackathon with a few other people, we worked on this tool. We ended up calling it CATS, again, acronym, so for Carbon Aware Task Scheduler. Basically, it's a little command line, again, all on GitHub, and you just say, I want to run a job for 3 hours. What is the best 3-hour window in the upcoming 48 hours? That gives you a time. And now we're working on saying, okay, how can we integrate that into task scheduling and workload managers? Because actually, a lot of the jobs we do, we don't really care if they run now or if they run tomorrow morning or even tomorrow afternoon. We usually have a bit of flexibility. Everyone runs their job on Friday afternoon because everyone's going home. And then they say, well, it's going to take the weekend. So actually, the best time to use a server sometime is like Sunday afternoon because all the jobs have concluded by then, which is a shame. If it's really low carbon electricity on Sunday afternoon, that's when we should run all the jobs, not Saturday morning. And so that's another thing we can do.
Community of practice. So I think I picked that up from your website. And what is that, and what exactly does it contain? What do you hope to achieve with it?
What I realized is that there was no place where people who are interested in computing sustainability or environmental sustainability when it touched to computing could share best practices, could share events they're interested in. And a lot of people came to me and said, oh, that would be great. When I give a talk or when I meet people at conferences, they say, oh, how can we keep learning about that? Because there are people everywhere interested in that, either RSCs or PhD students or postdocs or people who are doing research or people who are working in companies. Lots of people are like, I'm worried about climate change and I want to be mindful of the carbon footprint of the compute I'm doing. And so we try to build tools. But what was lacking is a place where everyone can exchange. And there are a few of these communities, for example, wet lab sustainability. So people who do experimental work. And wet lab sustainability is miles ahead of computational sustainability. So we're trying to catch up.
Is it? Okay.
Well, because people there have been mindful of single-use plastic for a long time. Because you can see it. You can see all the plastic you're throwing in all day. You can see the chemicals you're using. With computing, we don't see anything. I can start 100 GPUs from my smartphones by just logging on the HPC server. So because we don't see it, we've been kind of ignoring the problem. And people tend to think, oh, computer is green. Because we're behind, I thought, yeah, of course we need a place. So I had been putting it off for a long time because I didn't really know what was the best platform to gather people, what name to give it. And then I realized, well, maybe I don't need to figure it all out first. So if people want to join, if they go on our Green Algorithms website, there's a link there. For now, it's just a Google form. I guess depending when people listen to this, it will either still be a Google form or it will be a link to something slightly different, but there will still be a link to this community of practice. And the idea is just people who are interested, how can we give them a place where we can exchange best practices? Someone says, oh, I figured out that this packages in R is orders of magnitude more energy efficient than these other packages that maybe you didn't hear of. That's this easy savings. Or say, oh, this conference is talking about sustainability, maybe people are interested. Or here's a job about a green research software engineer that maybe people are interested. So, somewhere where we can just informally exchange, communicate around that, share knowledge. So it's really good tractions, actually. I was a bit surprised by it and really happy. So lots of people have signed up already. So I'm hoping in the next few weeks, I'll be able to come up with a proper structures. I think we'll probably do something hybrid where there will be a mailing list for people who just want to be on the mailing list, but also maybe like a Slack workspace or a similar workspace where it can be a bit of a forum where people can talk. And I'm hoping that can really grow for everyone who is interested in this topic.
Which hopefully will be many people. So you've mentioned we a number of times. How many people are involved in the kind of work that you're doing?
Well, in Cambridge here, it's mostly two of us. So I'm working with Michael Inouye, who is a professor of system genomics here in Cambridge. So he was my PhD supervisor, is now the PI of my lab. And so we've been kind of pushing this. And that has been great to have this kind of support, because one of the main things that comes when we talk about sustainability with people, computing or not, is, oh yes, of course I'm really interested, but I don't have the time to spend on it. I have a day job, I'm supposed to do my whole day. And people would say, yeah, sure, you can think about sustainability, but please do it in your own time. And so I've been really lucky here that the department just gave me the space and say, yes, if you want to spend half your time building sustainability tools, I have been able to do it. So that has been really lucky. But it is a really small scale. So this whole green algorithms is very much the two of us for the past 3 years. And when we started, Jason Greeley helped us build the tool initially. So it's a small scale project, hopefully with a lot of impact. So we're hoping to grow in the coming years. Attracting funding is a big one. So there isn't a lot of funding streams dedicated to this topic. So that's one of the things is, okay, how can we attract funding to be able to do everything we want to do? But there are lots of people thinking about environmental sustainability outside of just our lab. The CATS team is brilliant. So it's like 7 or 8 of us, RSEs and scientists all across the UK who have been working on that. There are more and more research teams around the world starting to think about it. Yeah. And obviously, there are all these people who are computer scientists who've been thinking about how to make hardware more energy efficient. And that goes back decades, so it's not new at all. What is kind of starting to get new is to take this to the users, to the scientists who are actually doing the work, to force them to think about it instead of just being a problem for sysadmin or hardware people.
Which is the education bit in greener, I guess.
Yes, definitely.
Well, and congratulations to the prize that you've won in Manchester, the collaborations function.
Yeah, the CATS tool won the hackathon, which was really nice.
Well, thank you very much for your time today.
Thank you. It was great.
If you want to find out more about green algorithms, go to the website. You'll find the link in the episode notes, which is where you also find the link to their calculator. I also included a bunch of other signposts, like for instance a link to the CATS estimator on GitHub, the Climate Aware Task Scheduler. And I hope you'll take a look. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.